Scientists have odious manners, except when you prop up their theory. Then you can borrow money off them. Mark Twain. Which is kind of a fun quote for today's module of Up and Down the Ladder. And with me today is Carl Fields. Carl is undergraduate here at Arizona State University. And we're going to go after a couple of questions in today's modules, which is what is the structure of matter? What is the atomic structure of matter? What are the phases of matter? What are the different forms that it kind of comes in? And how does energy get stored inside of atoms? So Carl, what is sort of the structure of matter at the atomic level?
So at the atomic level, you have basically everyday ordinary matter. It's made up of atoms. These atoms basically have a nucleus, and that's where this nucleus, where the majority of the mass is held, is at the center. Then you have these electrons that are not so much orbiting in a particular fashion, but kind of occupying a fuzzy cloud, so to speak, around the nucleus of the atom. And the order of these atoms are about 10 to the minus 10 actually meters, so they're very, very small. But that's kind of what makes up these different, what makes up matter that we see in everyday life.
Cool. So all atoms are about the same size, roughly? Order of magnitude estimate?
Yes, yes. So all atoms are about the same size. You do have some with larger nucleuses that make different size atoms, but they are around the same order of magnitude estimate.
How much smaller is the nucleus relative to the whole thing? So the whole thing's about 10 to the minus 10, and we have most of the mass in the middle. How big is that middle, so to speak?
So that middle does occupy a good majority of the size. It's about 100,000 times smaller than
the size of the atom?
The size of the atom.
Okay.
But it does maintain, like I said, it does maintain the good majority of the mass for the entire atom there.
Okay, great. So that's a little bit about the size of the atoms, the size of nuclei. But as you mentioned, that there are different types of atoms, and what do we mean by that, and how does that relate to like the periodic table?
So basically, what we have is for each atom, there are a certain number of electrons that can fit in what's called an atomic orbital. So for the ground state, for a particular atom, you can hold up to 2 electrons. And beyond that, they have to start occupying larger and larger, or different orbitals. There's only a certain amount of electrons that can fit in a particular orbital. And that sort of determines what properties a particular atom may have. In addition to that, the nucleus, the number of neutrons and protons that are in the center of this nucleus determines basically the intrinsic property of the atom itself. More neutrons, more protons means a heavier atom, means a different element, which kind of traces back to what we see in the periodic table and what determines the atomic mass for that atom.
Okay, so let's take a couple of examples. How many protons are in hydrogen?
So hydrogen has 1 proton.
How many in helium?
In helium has 2 protons.
Lithium?
Lithium, that has 3.
Okay, so must be the number of protons that determine the chemical element. Is that right?
Correct. So you have the number of protons and the number of neutrons, and basically those together determine the structure of the atom itself, basically, and what we can trace back to the periodic table of elements.
So what is the charge on a proton and a neutron?
So the proton's positively charged. A neutron is a neutral charge, and the electron does have the negative charge.
So in something like an atom, they're generally electrically neutral.
Correct.
Okay. Can I add so if I have an element which is determined by the number of protons, then what is the number of neutrons? It's always, for example, carbon, right? Carbon-12, we're made out of carbon-12, and carbon has 6 protons. Mm-hmm. But I hear things like carbon-14 dating, there's carbon-13. What determines, so it's all carbon, so what's the difference between What are those called?
So what happens is, say for instance for carbon, like you mentioned, you may have a atom of carbon, but you can also have carbon that has more isotopes than, or excuse me, more neutrons than the typical carbon-12. So for instance, you may have a carbon atom that has one extra neutron, and that makes it carbon-13. So it's basically heavier carbon. And so you can have these different what are called isotopes, which are basically atoms, but they may have these additional properties where, additional neutrons that make them more massive and make them exhibit different, basically, properties than their less massive counterparts.
Right. So, for example, carbon-14 is often used in radioactive dating components. Are all isotopes radioactive?
So all isotopes are not radioactive. However, what may be particularly attractive of carbon-14, as you may, is it may have a specific decay rate that may allow us to really nail down that time frame when we're trying to look at the particular scientific phenomenon that we're looking at.
So it's like a clock, a chronometer.
Yeah.
As we measure stuff.
Correct.
Okay. So we have atoms, and we take atoms and we put two of them, at least two of them together. We make molecules, and then we start putting various molecules together. And does matter have different phases? And if so, what are those phases, and what are the differences of those phases?
It's interesting that you asked that. So matter actually does have 4 unique phases that we can think of. So we have solid matter, we have liquid matter.
Like your coffee.
Yeah, I mean, my coffee here have liquid matter. If I heat it up, it goes to gas and it can evaporate.
Is there steam coming off your coffee?
It's not actually. I like my coffee room temp. Kind of strange. But then if I was really weird and I wanted to get that, go beyond that, I could drink some plasma coffee perhaps. It'd be a little hot, but it definitely...
Plasma. What's a plasma?
So plasma is actually, it's one of the phases that's somewhat beyond a gas. So when you take a gas and you heat it to extreme temperatures and densities, it takes on this state known as plasma that exhibits very particular properties that differentiate it from gas.
What happens to an atom in a plasma?
So in the plasma, an atom becomes ionized. And so basically it does, like I said, it does basically take on these different properties that normal gas would, for instance, of hydrogen or helium or something like that.
So plasma kind of becomes like this soup of
electrons. So it almost takes on this different form of matter that's not so much liquid as we know as general water or something of the sort, but it's like you mentioned, almost like this electron soup. We typically see it inside the interior of stars.
Okay. Are there examples of plasma here on Earth?
So one example you can think of is electricity. And so when you do have this very quick burst of, for instance, lightning coming down from the atmosphere, for a very brief second you may see properties that exhibit that of plasma, up near the surface of the clouds that do create these lightnings.
How about aurora?
Aurora as well. So for instance, in the northern hemisphere near Alaska and whatnot, you see these basically light structures, if you will, in the clouds of the different properties that this plasma is taking on just from the different isotopes in the atmosphere that you see.
Okay. You mentioned that there are these 4 properties. We have solid, liquid, gas, and a plasma. And what is the common thread between those? How do I go from one phase to another? What is the dominant driver of that? So
it's interesting that you asked that, because it would seem that there's a lot of different ways that you can actually reach these different phases of matter. But one of the really main driving factors is temperature.
Okay.
Going from coldest to hottest, you have solid, liquid, gas, and plasma. And that's really the main factor that determines how we go from these different transitions of phases of matter and how we can sort of begin to look at what type of properties we can expect these to exhibit.
So it's kind of like a temperature sequence.
Yeah, it's definitely a temperature sequence. That's really the main thing that can kind of nail down how you determine where your transitions will take place between these different types of matter.
Okay. Let me loop back to something you had mentioned earlier. You mentioned that you have an atom, and in the innermost orbital you can hold 2 electrons, and then farther out on the next orbital you could hold 8, and so on. How many of these orbitals are there? Are there an infinite number? Are there only 2 or 3 or 4? How many orbitals, how many steps, how many energy levels are there?
So the amount of energy levels basically is determined by the nature of the nucleus, and that's really, it boils down to a quantum mechanical effect as to why the electrons only occupy a certain amount of orbitals. Basically, but there is a finite amount of these energy levels, and beyond that, the atom, once it exceeds this threshold of orbitals, becomes ionized, and the electrons actually they're free from the atom. They're unbound.
They can become plasma at that
Correct.
point.
Correct. They are unbound, they're ionized, and they can become plasma.
Okay. So I've got this energy level, and I've got some sort of a rest energy state, and I'll have some next orbital, which is at a higher energy state, because it's farther away from the nucleus. Can you talk a little bit about how an electron makes a transition, let's say, from the ground state up to the next higher energy level?
Sure. So one of the interesting things, and this was very shocking at the early 1900s, was that these energy levels, they're very discrete. They're not a continuous energy. So, for instance, the energy required to eject a photon, for instance, from a sheet of metal. You can shine a light on it, and it can, the intensity of the light doesn't exactly reflect the amount of photons that are ejected. It's a discrete, once you reach a discrete value for a particular energy, then you will have this photon emitted, as opposed to a continuous spectrum of that. And so that's analogous to the atoms that we see. It takes a certain amount of energy for this electron to go from one orbital to the next orbital. It can't make that jump with some amount of energy that's in between that or below that. It needs a very particular amount of energy to make that transition.
So let's say I have some ground state here, and I've got some energy level up here, and we'll just call that difference 10, just in some energy units 10. So let's say I come in with some energy, either in the form of a photon or a collision, whatever it may be, and suppose that I can inject 5 units of energy. Does the electron go to that next level? Does it go only halfway? It's got half the energy. Can it go halfway, or does it just not accept it at all?
It actually doesn't budge.
Okay.
And that was very intriguing to scientists early on when, why is this not making that transition? It has some energy, what's going on there?
Well, what if I come in with more? What if I come in with 12?
So with 12, what will happen is you do have this transition. Say, for instance, if that threshold was 10, you have the electron make that transition, but it will only use that 10 that it needed, basically, for that transition. The other 2 will go into either thermal energy or something of the sort.
Okay. So we have these very discrete energy levels that can only be populated. So that's going up. How about coming down? So let's say we have an electron in a second excited state, and it goes down 1 state. Where does that energy go? What does it do?
So it's interesting that you mentioned that. It's basically the same as the forward process, except what happens is when this electron, for instance, may go to a lower energy state, it will emit a very discrete amount of energy that's very particular to the amount of energy it would take to go from the state that it went to back to that original energy state. And so that transfer of energy up or down is the same between these different orbitals.
Okay. So when it emits a photon on the way down, you said it has very specific energy, and that means it has a very specific frequency. It has a very specific wavelength, meaning it has a very specific color.
Correct.
To that light. Huh. So every element has a unique rainbow of colors associated with it?
Yeah, and so, for instance, a lot of times you can use these properties of, for instance, say, electron goes to a lower energy state and emits a particular color photon. Associated with that photon is, as you mentioned, a particular wavelength, and so we can really utilize that to determine the chemical composition of, molecular clouds, stars.
How about closer to Earth? What is that good for Earth if I want to use this technique of picking up the rainbow of colors associated with an element?
If you have a sample of matter that you're unsure what its composition is, then you can sort of determine, what it's comprised of by looking at these different decay processes and whatnot.
Right. I think there's various television police shows on what is it? CSI. Where they'll do that. They'll take a piece of unknown material, rubber from a car or something, and you burn it, you make it light up, and then you take that light and you put it through a prism, so you make the rainbow, and you'll see this pattern of lines. And so in some sense, you're really seeing atoms. You're seeing atoms make that transition. So if anybody ever asks you, can you see an atom? The answer is yes, you can. You'll see them making their transition, and you see a very specific color coming out from those atoms. Well, that's cool. How about a laser? How does a laser work with energy storage? And well, in particular, energy storage and energy drop.
So basically, a laser, what it does is it takes this energy and it focuses it into a particular beam, if you will.
Sure.
It amplifies the energy emitted by these electrons as they go to lower states, and then basically it sort of diffracts as it travels outward. But basically, it's a coherent beam of light that focuses this energy at a particular wavelength for a number of different uses.
Let me phrase the question this way. We said so we have these two energy levels, and so when an electron drops down to an energy level, it emits a photon of a very specific color, a very specific frequency, a very specific wavelength. And so is a laser a bunch of different wavelengths? Is a laser all the same wavelength?
So a lot of times you'll see a very particular transition taking place, which means you'll see a very particular wavelength emitted.
Okay.
For instance, a red laser beam you see often. It's because you see there's a particular transition taking place for this laser that emits that one discrete monochromatic, as they call it, laser that you can use. So basically, it's that one transition that we're seeing again from that electron to that lower level energy state that's emitting that particular wavelength of photon and light.
In the case of a laser, you have a whole bunch of electrons. They're all in the same state, all falling down and then getting pumped back up and all falling down. And so you're seeing this continual pumping between let's say the ground state and the first state, such that they all release one color of light.
Correct.
That's cool. That's cool.